All right, so welcome back. We're going to be talking in this video about tolerances. So we've talked previously about unspecified tolerances and how they interact with parts. We've talked about concepts like MMC and LMC. In this particular video, what we're going to be doing is we're going to be looking at accumulated tolerances. So specifically, we're going to be tying this in with dimensioning. We're going to be looking at some different styles of dimensioning, chain dimensioning, a broken chain dimensioning, and a datum dimensioning method. So we're going to be going through those as we talk about this here. So we have a part, let's say it's a steel plate, and this steel plate has 5 different steps, if you will. So let's say that we have dimensions on this. Something like that, okay? So this first method we're going to be looking at is called chain dimensioning. It's called chain dimensioning because it simply is linking one dimension off the next, off the next, off the next. So let's go ahead and throw some numbers up here. So let's say that this one here is 1.000. The next 3 are going to be 1 with a 2-place decimal, and the last one here 1.000. So in this case, the first and the last ones have a 3-place decimal. The 3 middle ones have a 2-place decimal. And these will correspond to our unspecified tolerance block on the title block. So a 2-place is plus or minus 0.01. A 3-place is plus or minus 0.005 or 5 thousandths. So if we look at this method, this is called chain dimensioning. What we're looking at is how these dimensions will have this tolerance or this wiggle room, and when one is measured off the next, which is measured off the next, and so on, what these tolerances will do is they will accumulate up really large or really small. So in this particular case, if we were to look at the overall size of this plate, so 1, 2, 3, 4, 5, it should be 5 inches long theoretically, but with the tolerances you have some wiggle room in there, so it may be a little bit longer, a little bit shorter. So in this particular method of dimensioning, a lot of times what you'll see, and I'm going to show this in a different color, so hopefully you can see it better. A lot of times what you'll have is you'll have what's called a reference dimension. A reference dimension will be like a parenthesis, something like that. If you ever see a dimension with a parenthesis around it, what that means is that does mean a reference dimension, which means that this is not controlled by the tolerance. This is not dictating specific exact part sizes that the tolerance should dictate or override, but rather it's just there as a quick and easy reference for you. That's why it's called a reference dimension. So in this particular case, what controls the exact size of this part is going to be these dimensions with the tolerances that they're associated with in the unspecified tolerance block. This reference dimension just gives you the quick idea that plate should be about 5 inches long. Okay? So what we're going to do now is we're going to calculate up the maximum that this plate can be and the smallest that this plate can be. So if I walk through this process here, I'm just going to write up here max, okay? In the max case, each one of these have tolerance. So I'm going to write them here in green. This one is a 3-place, so the 3 places plus or minus 0.005 and plus or minus 0.005. So these 2 end ones are plus or minus 5 thousandths. The 3 in the middle are a 2-place decimal, so the 2-place decimal in our unspecified tolerance is plus or minus 0.01, plus or minus 0.01, plus or minus 0.01. So whenever I go to add these up for the maximum size, since these are all chained together, hence chain dimensioning, because of that, what we want to do is we want to go max size plus max size plus max size plus max size, and that's going to push each edge the farthest down the row. So I'm going to go 1 point and then plus 5 thousandths, 0.005, plus 1.01, 0.010, the next one here 1.010, the fourth one 1.010, and the last one 1.005. And here I'm just going to add these numbers up. When we add them up, There's 5, 10, 20, 30, 40. So 5.040. In this particular scenario, that's the max length that this part can be. Okay? So that's as long as that part can be. Now, if we were to look at it on the other end, how short can that part be? If we look at the minimum size, we're going to do the same thing. We're just going to subtract out the difference here. So the 1 inch dimension minus 5 thousandths gives us 995. So 0.995 plus 1 inch minus 0.010 gives us 0.990, 990, 990, and the last one there, 995. And in this particular case, we'll add them up again. So 995, 0, carry the 1, 1, 2, 3, 4, 5. So 4.9, what does that come out to be? 5, 6, there we go. Okay. And so the smallest plate that can be is now 4.960. Okay? Notice this one here is 40 thousandths over the 5 inch mark. This one here is 40 thousandths under the 5 inch mark. So if we were to talk about our range, okay, that overall range is that number minus that one. So 5.040 minus 4.960, which gives us 0.080. Okay? So, with this here, we've now calculated up the total tolerance range that part can be. This is one way of dimensioning. Remember the rule, you want to design things that have the loosest tolerances possible where it's still fully functional and safe and won't break after 3 uses, you know, that type of thing. The reason for that is we can always make tolerances tighter, but the tighter the tolerances, the more your cost goes up. So as engineers, as designers, you need to keep that in the back of your mind. You want the tolerances to not be excessively tight unless they need to be. If they need to be, that's fine, then make them excessively tight. But many times you don't have to have super tight tolerances unless it's a very critical application. Most of the time you can have looser tolerances, and remember, the looser the tolerance, the less that it costs, so the cheaper it is to make. But you don't want to have them so loose that, you know, it causes malfunctions and the parts to break. So this here is one method for dimensioning. It allows you to be able to have loose tolerances all the way across the board. It uses a reference dimension, which is just a quick reference for you, but this does not have any bearing on the actual part with the tolerance specifications. All that's required by the main dimensions.